Hello everybody, getting ready to do lesson 2.3 today for pre-calculus math, part 1. And 2.3 part 1, real zeros of polynomial functions. We have 70 points here of classwork, and you have 8 points to put in your notebook today. Note-taking guides, I can provide those for the classwork. Contact me. Using long division to divide polynomials by other polynomials, and using synthetic division, and then using the remainder and factor theorems. This is chapter 2. Teachers, today's bell work is we got a word problem here with this function here where g is the height of the tree in feet and the time is 2 is less than or equal to the growth, the age of the tree to 34 in years. Use a grapher to graph this function, and then this point is called point of diminishing returns. So estimate the age of the tree when it is growing most rapidly. So graph it and do that. Give your students about 5 minutes for that. Okay, welcome back for the solution to our bell work today, and we're going to estimate the the most rapidly part of the growth, and it's up to you. I mean, it seems like actually here is the most rapid growth area. Point of diminishing returns will be 15.2, 27.3. So that would be over here somewhere, 15.2, 27.3. That would probably be the vertex. That would be right here. Now on your graph, on your scaling of your graph, you need to rescale it, students. I mean, you can make these worth 2 points here instead of just 1. So 2 for up to, this would be 20 up here. So this would be about 18. So something like that. I'd rescale it. And then 15.2 years is the point of diminishing returns. That would be your vertex. Okay, moving on to our first notebook page here. Long division of polynomials. Consider this graph here. This is a graph of this third degree polynomial here. And so because f of 2 equals 0, this would be an x-intercept here. You know that x equals 2. Yeah, f of 2 equals 0. We know that from looking at the graph and using your trace feature and your intersect. And that x minus 2 would be a factor of this polynomial. We know that it will be x minus 2 would be a factor here for this polynomial because of that intersection. So knowing that, it would yield a second degree polynomial when you factor x minus 2 into the quotient. Your quotient would be a second degree polynomial. To find qx, you can use long division of polynomials. So at first we used graphing. Now we're going to use long division because we know x minus 2 is a factor of that polynomial. So to do that, let's do another situation here. We've got this third degree. So that was what was yielded by our graphing, and then we have this now as a situation here by x minus 2 and use the factor to, okay, so example 1 here. We're going to do a long division here by x minus 2. So first, x will go into 6x cubed, 6x squared. So we're going to multiply now 6x squared by our divisor, and then we get 6x cubed minus 12x squared. And then we subtract. These cancel out here. And then in this situation here, when we subtract 12x squared, it becomes positive. And then we combine, and it would be 7x squared. Then we drop our 16x down. 7x squared plus 16 Now x minus 2 will go into 7x squared how many times? 7x. 7x, negative 7x times x would be negative 7x squared. And then negative 7x times negative 2 would be positive 14x. Change signs and add. These would cancel. And then 16x minus 14x would be 2x. And we drop down to negative 4. And then our x will go into 2x twice. And then, so where's our 2 at? There it is. So we multiply 2 times x minus 2. We get 2x minus 4. Change signs and add. And then these cancel each other out. So we have a remainder of 0. So we know x minus 2 is a factor of this polynomial up here. And then here is the graph here of this third degree polynomial. We determined that positive 2 was a factor. And then we have this 6x squared minus 7x plus 2 now. We have a quadratic now. So to further factor that, x minus 2, we know that we have this situation here. So x minus 2 times 2x minus 1, 3x minus 2. So this would be the fact we get these two binomials from this quadratic here. So note that this factorization agrees with the graph. So 2x minus 2 would be 1/2. This would be 1/2. Or rather, yeah, it would be 1/2 here. And then this over here would be 3x minus 2. This would be 3. Would be 1 and 1/2 would be here. This would be 2. Or 2. I guess they're saying this is 2 here. So this is your positive 2, and then these are your other factors here. Okay, 3 intercepts occur at 2. We know that from here. And then 1/2. This would be the 1/2. And then this would be the 2/3 here. What did I say up here? This would be 2/3. So this would be 1/2, and then this would be 2/3 there. Okay, into our first guided practice here. We're going to use long division on this thing here. We're going to divide by x plus 3. And then this is your students down here. You have this quadratic going to divide by x minus 4. Let's do this guided practice first now. So when we do that, x plus 3 divided into 2x squared plus 10x plus 12. So we get 2x plus 4 as our quotient here. 2x times x, 2x squared, then 2x times 3 would be 6x. Change signs and add. Then we get 4x plus 12, then we get 4x plus 12, we get a remainder of 0. So this would be this would be a factor, and then this would be a factor of this quadratic here. That would be how you would do it using the long division method for that. And then so 2x squared plus 10x plus 12 divided by x plus 3 would equal 2x plus 3. X cannot equal negative 3 in this situation here. X cannot equal negative 3 for this to work. Okay, so in example 1, x minus 2 is a factor of the polynomial. Remember this third degree polynomial here. X minus 2 is a factor. So it's 6x cubed minus 19x squared plus 16x minus 4. So now in example 1, x minus 2 is a factor of this thing here. And the long division process produces a remainder of 0. Often long division will produce a non-zero remainder. For instance, when you divide x squared plus 3x plus 5 by x plus 1, you obtain this, you have a remainder here of 3 when we are using long division here. So what do we do with that remainder? when we've divided this by this. Here's our quotient, here's our dividend, there's our divisor, and then our remainder. But we end up with 3 as a remainder. So we have 3 as a remainder, equals x plus 2, and then plus 3 over x plus 1. So this would be the way that you would write your remainder. You would, when you divide this quad by this divisor, you get x plus 2 plus 3 over x plus 1. Dividend, quotient, divisor is down here. And then here's our divisor, but this whole thing here is your remainder. This implies that x squared plus 3x plus 5 equals this here. It implies that. Multiply each side by x plus 1. So if we multiply everything here by x plus 1, this will cancel out. And then this will cancel out, and then you have this left when you multiply through by x plus 1, which illustrates the following theorem called division algorithm. The division algorithm, if f of x and d of x are polynomials such that d of x does not equal 0, and the degree of d of x is less than or equal to the degree of f of x, then there exists unique polynomials q of x and r of x such that f of x would equal d of x times q of x plus r of x. So here's our dividend, there's our quotient, here is our divisor, and guess what? There's our remainder. So that's basically the idea behind this algorithm here. Where r of x equals 0, or the degree of r of x is less than the degree of d of x, or divisor. If the remainder r of x is 0, then d of x divides evenly into f of x. That's kind of like the idea there for that. So the division algorithm can also be written as f of x over d of x equals q of x plus r of x over d of x. So whatever remainder is left from this situation here gets tacked on over here. If it's 0, then it's redundant. But if it's not 0, then the way that you would write your quotient would be like this. In the division algorithm, the rational expression f of x divided by d of x is improper because the degree of f of x is greater than or equal to the degree of d of x. On the other hand, the rational expression r of x over d of x is proper because the degree of r of x is less than the degree of d of x. So basically it wouldn't be in simplest form. In this situation here, r of x is proper because the degree of r of x would have to be less than the degree of d of x, and then up here it wouldn't be. It would have to be reduced to be a simpler form of that. So moving along here with this knowledge that we have now of all these algorithms. Example 2, long division of polynomials. Divide 8x cubed minus 1 by 2x minus 1. So here is our divisor here, 2x minus 1, and then this would be our dividend right here. So to divide this in long division, because there's no x squared term, there's no x squared term here, and we need to fill that in, and there's no x term either. So we have to do that in our long division format here. You need to line up the subtraction by using zero coefficients or leaving spaces for the missing terms. So this would be the way that your dividend should look. 8x cubed plus 0x squared plus 0x minus 1. That would be the way that you would start this off. And then here's your divisor. Okay, so 2x will go in 8x cubed, 4x squared times, and then we multiply through into our divisor now from our quotient 4x squared times that be 8x cubed minus 4x squared. And then we change signs and add. These cancel out. This becomes positive 4x squared. We drop this down. So now we have this 2x will go into 4x squared. Again, 2x times. So 2x times 2x will be 4x squared. And then minus 2x times negative 1 being negative 2x. Change signs and add. These will cancel. And then this will become a positive 2x. Drop this negative 1 down. So now we have 2x minus 1. So we can just multiply now by 1. And then we have a remainder of 0. So this would be our two factors now of this third degree polynomial. So 8x cubed minus 1 divided by 2x minus 1 equals 4x squared plus 2x plus 1. X cannot equal 1/2. So that would be the way to do that. So let's try this one here. This is our guided students. This is you. So we're going to divide 7x cubed plus 3 by x plus 2. So to do that, x will go into 7x cubed, 7x squared time. We multiply through. We get 7x cubed plus 14x squared. Change signs and add. Then we get negative 14x squared. Drop this down, although in this situation here, we have negative 14x. We don't even put that here. You can do that, but I would. I would put the 0x just to keep track of things easier. And then x will go into negative 14x squared, negative 14x times. So you multiply that through, you get this negative 14x squared minus negative 14x times 2 be negative 28x. Change signs and add. So now we got 28x plus 3, drop our 3 down, multiply through by 28, and we get 28x plus 56, change signs and add, and we have a remainder now of negative 53. So with that situation, we have 7x squared minus 14x plus 28. And then since this is negative, this will be negative here. Negative 53 over x plus 2. So this would be our quotient in this situation here. Dividing this polynomial by this divisor. Okay, into example 3, long division, another one here. We got this situation here. We're going to divide by this quadratic. So here's our divisor. Here's our divisor. Then our dividends here. And let's see, x to the fourth, x cubed, x squared, x. So we have all of our descending powers here of x. We do have that. But is this in standard form of a polynomial? No. So I put it in standard form before I would do it. Begin by writing the dividend and descending powers of x. So this is what this is. Here's your dividend here in descending powers of x. And then x squared will go into 2x fourth by 2x squared times. Then we multiply that by our divisor here. And we get 2x to the fourth plus 4x cubed minus 6x squared. Change signs and add. These cancel, and then here we'd have a positive x squared, drop this down, plus 3x minus 2. So for this, we're going to multiply through by 1 times x squared plus 2x, and then minus 3. So this is what we would have underneath. Change signs and add. These will cancel, and then this will become x plus 1 now. This will be a positive 3. So we have a remainder here of x plus 1. So when we have this here, this is our quotient here. When you divide this by this, you get 2x squared plus 1 plus x plus 1 over x squared plus 2x minus 3. This would be your quotient for this division problem up here. We have another guided practice now to do. We're going to divide this by this. Students, this is yours down here. Okay, for a guided practice, this situation here, we put a 0x in here because we're missing an x term here, so we just stick this in here to substitute as a placekeeper for that. So 2x squared plus 0x plus 1. 2x squared, we're going to 6x cubed, 3x times. Then we multiply through, and we get 6x cubed plus 0x squared plus 3x. Change signs and add. These cancel. And then this just becomes 10x squared. And then this becomes negative 2x. And then we drop down our 8. We multiply through now 2x squared. We're going to 5x squared 5 times. Multiply through. And we have this here. And then this is negative 2x. Change signs and add. Negative 2x plus 3 here as our remainder. So our quotient will be here for this division here. Here is your quotient for that problem there. Okay, another notebook entry here, students. There's a nice shortcut, synthetic division, for long division of polynomials when dividing by divisors of the form x minus k. The shortcut is called synthetic division. The pattern of synthetic division of a cubic polynomial is summarized as follows. This goes in your classwork. This will be on your classwork sheet. Synthetic division of a cubic polynomial. To divide this by this, use the following pattern. So we can stick the negative of k out here, and then we have kind of like a inverted long division symbol here. And we drop down a, and then we multiply k times a, and we put that underneath b, ka, and then we add ka to b, and then for a remainder there we multiply by k, put that over here, add, drop down, multiply by k, and then put that over here, add, and then here's your remainder. That's the general form for it. So the coefficients of dividends, and then the remainder here. And these are the coefficients of your new quotient now. So vertical pattern, add terms. So the vertical pattern here, you would add terms. You wouldn't change signs and add. You would just add them together. Then the diagonal pattern would be multiplying by k. So when you go diagonal here, these are products of k times that, k times that, k times that. And then your remainder, you stop there. You don't multiply your remainder. So let's get an example of that now. Using synthetic division, use synthetic division to divide this by this. So let's set up an array here. Here's our array. Then we have coefficients. These are coefficients for this polynomial. X to the fourth is 1. We don't have a cube, so it'll just be 0 cubed. And then negative 10x squared, and then negative 2x, and then plus 4. Here's our constant. And then here's our pattern here of coming up with our new quotient. Note that it's 0. We note that the 0 is there. So we drop down our 1. That's our first step. Then negative 3 times 1 will be negative 3. Negative 3 and 0. And then we just add. We don't change signs. We just combine these two. We get negative 3. Then negative 3 times negative 3 would be 9. And then we just add. And we get negative 10 and 9 would be negative 1. Then negative 3 times negative 1 would be positive 3. And then we just add here, and we get 1. And then negative 3 times 1 would be negative 3. And then we just add here, and we get 1. So that's our first example of synthetic division. So when we get through with that, we have our dividend here of x cubed minus 3x squared minus x plus 1. And then we have a remainder here of 1 over our divisor here. So a remainder will be 1 over x plus 3. So here is our quotient of this division problem here using synthetic division. So there's our x cubed, there's our 3x squared, negative 3x squared. There is our, okay, we get to see that twice. And then here's our negative 1 for x, and then negative 1 for x. And then here is our 1. That's our constant term for that. And then there's our remainder. Oh, we could see there everything twice, I guess. So that is our remainder for that. Okay, so now our guided practice using synthetic division. We're going to divide this by this. Okay, so doing our guided practice here for this, here is our setup here for synthetic division. We change the sign here and put it out here as our divisor. And then here is our original dividend here, 3, negative 17, positive 15, negative 25. Drop down our 3, multiply 5 times 3, we get 15, then we add, we get negative 2, 5 times negative 2 would be negative 10, we add, we get 5, then 5 times 5 would be 25, so we have a remainder here of 0, so we know this is a perfect factor here with no remainder. So we multiply, when we divide this by this, we get 3x squared minus 2x plus 5 with no remainder. And x cannot equal 5 in this format anyways. So moving on to the remainder and factor theorems. The remainder obtained in synthetic division process has an important interpretation as described in the remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is r equals f of k. This tells us that the synthetic division can be used to evaluate a polynomial function. That is, to evaluate a polynomial function f of x when x equals k, divide f of x by x minus k. The remainder will be a function of k in that situation there. So what does that mean? Well, using the remainder theorem, example 5, use the remainder theorem to evaluate the following function at x equals negative 2. So f of x equals 3x cubed plus 8x plus 5x minus 7. Using synthetic division, you obtain the following. So here's our array here for synthetic division. We're going to evaluate this at negative 2. Then here are our coefficients down here. Drop down 3 times negative 2, we get negative 6, add. Negative 2 times 2 is negative 4, add. Negative 2 times 1 is negative 2, add. So we have a remainder here of negative 9 when we divide by negative 2. So r is negative 9. You will conclude that f of negative 2 would equal negative from that situation. So you could find like coordinates of a graph. You can check this by substituting x equals negative 2 in the original function, r equals f of k. So when we put in negative 2 in there, we get this situation here, and then we keep combining simply, and we get negative 9, sure enough. So when we plug in negative 2 in the function, we get negative 9. So let's see what we can do with that up here. In this exercise, we're going to plug in f of 1 in here. So, and then let's check using a graphing calculator. So we divide through by 1. We have a remainder here of -2. So that would be a point on that graph. So that is 2.3 part 1 of pre-calculus math. If you need note-taking guides or worksheets, quizzes, or tests, email me here. Thank you very much.